Welcome back, my structural analysis friends. In today's lesson, we're going to be looking at yet another method for solving for the deflections of beams. This is a method that comes from our category of geometric methods and is known as the conjugate beam. It's super simple to use and super simple to analyze, so let's get started. The conjugate beam method is kind of a time-proven method for solving relatively simple beam structures to be able to solve for deflections and slopes. It was created by Otto Moore, yet again, in 1868, and it's a more convenient method than the moment area method. If you remember back when we did our moment area video, we were talking about that we were kind of limited on the loadings that we could put onto our beams. It had to be, pretty much a concentrated load to be of any real use. That method had problems with, higher order functions, constants, or linear, or even parabolic loadings. It was just difficult to do. You could do it, but it was just difficult. This method solves that problem. And so all that you have to do is it's much more convenient than moment area. All you do is you draw an M over EI diagram again. That's what we did before. So if you need help with how to do that, go back and look at our video on moment area. We kind of explain the process. And here's what his idea was. The basic idea is that we can use relationships between load, shear, and moment and then transform them to M over EI, slope, and deflection. Now, in most classic literature, you'll see deflections written as a Y variable, as a function, or sometimes given as a delta. I choose to use a little bit of both, so you'll see me kind of use both on those. So here's what we know. From our shear and moment diagram relationships, we know that the slope of our shear diagram was related to the load, and that the slope of the moment diagram was related to the shear. And so by that means that the moment was a second derivative. The second derivative of the moment was corresponding to the load that's being applied. So that's kind of interesting. Now, if you remember in our moment area derivation, we showed that the first derivative of the slope was also M over EI. And we know that the first derivative of y, or our deflection, is theta, or the slope. So by the same logic that we used up here, we can say that the second derivative of the deflection, y, with respect to x, is M over EI. And if you remember, this was that governing differential equation that I said kind of makes the world go around. This is an important equation in structural analysis. But if you kind of look at this, I have an M on this side that I know, and I have an M up here. So by this logic, then, there's a derivative of y that is related to the load. And in fact, this is another method. It's called I guess it's the quadruple integration method that can also be done. It's sometimes taught in undergraduate classes, not very often. We're not going to cover that one in this video, but there is a relationship between deflection and load. So that means that if you think about it, load, shear, moment, slope, and deflection are all interrelated. Now, here's the mapping that Moore came up with. He says, well, if I kind of look at the orders of the derivatives on this thing, that the shear in this equation is kind of like the slope in this one. And that the moment in this equation is kind of like the deflection in this one. And so he came up with, so all he would have to do to be able to analyze this, we know how to handle the first one when we do shear and moment diagrams, that if I can do a transformation and remap onto what we call the conjugate beam, all I have to do is change the boundary conditions, and I can come back up and reapply the same shear and moment methods to it. It's a pretty cool concept if you think about it. Now, what are the mappings that we have to do? It's really easy. There's about 6 of them that we have to look at to be able to kind of redefine. All we're going to do is we're going to take our original structure and we're going to change the support conditions to something new. All right, so let's start with the first one. I fixed support before on the real system. We know that the boundary conditions on this were that theta had to be 0 and delta was 0. After using the same ideas up here, then after, to come up with a theta of 0 before will correspond to a moment of 0 after. and a delta of 0 before would be a shear of 0 after. Well, if we look at those conditions, that represents a free end. So our new structure, wherever it was fixed, will now be a free cantilever end. Okay. All right, so I know it's a little, just bear with me here. We'll get through these and then I'll show you how it works. It's really, really easy if you can just memorize these mappings. Okay, the simple support, play the same game. Okay, we know that the boundary conditions for a simple support at this location here was that theta was not equal to 0 because this thing can rotate, but that delta was 0. So a theta not equal to 0 before is the same as a shear on the conjugate not equal to 0 after. And a delta equal to 0 is a moment equal to 0. Okay, again, this is the real system, this is the conjugate system. And so we know shear not equal to 0, but m equal to 0, that represents a simple support. So wherever you have a simple end support, nothing changes, you keep it the same. Okay, let's go look at a free end. This is kind of the flip of the cantilever end. So my free end on this then would be looking at this point here. We know that theta definitely is not equal to 0, and delta is definitely not equal to 0. Will correspond on the conjugate system of v not equal to 0 and m not equal to 0. Okay, and because this is unrestrained and can do whatever it wants, this is going to be fully restrained as a fixed end on this. Now this one's we're going to be kind of careful with this. We're going to see these boundary conditions again on the next one. Okay, but there's a kind of some logic that applies in this. Okay, now we have internal hinges. Okay, what's the behavior on an internal hinge? Well, theta is definitely not equal to 0, and the moment is not equal to 0. Okay, but if you think about this, while theta there's no restraint, there is a little bit of delta restraint that if this side wants to move down, this guy's got to hold it up. Now, it's not fully free to move, and it's not fully restrained. It's kind of an in-between status. Okay, so there is some restraint. So our idea of using those boundary conditions to call this fixed doesn't necessarily apply. Okay, so, but we do have the same boundary conditions, v equal to 0 and m not equal to 0, sorry, v not equal to 0, both of them are not equal to 0. Then if there is some restraint, then this thing can rotate a little bit, has a little bit of shear, can have some moment in it, that this then represents what would be a continuous support. Because if you remember back to your shear and moment diagrams, a continuous support, we had moment values possible over, directly over those support conditions. Okay, so that's our mapping for the continuous support. And likewise, we can do the continuous support, that now we go the other way, that now theta is not equal to 0, but delta is equal to 0. Well, that maps onto a v not equal to 0 and an m equal to 0. Okay, well, an m equal to 0 where a shear is not 0 implies a hinge. Okay, and so that's our internal hinge mechanism. So this one, an internal hinge becomes a continuous support on the conjugate, and then a continuous support on the real becomes an internal hinge on the conjugate. Okay, so that's what we have for those. So those are our methods. Those are our 5. I think I said 6 earlier, but there's actually only 5. All right, so here's the method, and then we'll get into some examples pretty quick. Okay, here's the basic procedure. Just like you did before, you're going to draw the shear and moment of the original structure. Okay, we're then going to transform the original structure to a conjugate system using those mappings that I just showed you. Okay, basically you're just remapping the supports and the hinges. We're going to take the moment diagram of the original structure as the loading on the conjugate structure. This is the one that's kind of unusual. Okay, and I'll show you what that means here in just a second. Okay, and then all we have to do is on the conjugate beam solve for the moment and the shear at the point that I'm interested in. Okay, and when we find those values, those map back to be the delta on the real and the theta on the real, the slope on the real of the real behaviors using those mappings that we had. So this is where it works. Okay, so it's pretty cool. The sign convention is our classic right-hand rule. We're going to go up positive, to the right positive, counterclockwise positive. Okay, and then the basic rules for applying, for analyzing our results and applying the load are as follows. A positive area on an M over EI diagram of the real structure is applied as a positive or upward load on a conjugate. Now again, we're only looking at doing this for beams. Okay, so a positive load. So you will get loads that will act upwards on the conjugate system. Okay, a positive shear of the conjugate implies a positive slope of the real. Again, positive meaning counterclockwise. And then the positive M of the conjugate implies a positive or upward deflection of the real. Okay, so it's positives to positives. There's no funny business on the mapping of the signs. All right, so let's give one, a fairly simple one, a try real quick. Okay, so what I have is I have a beam here that is of 2 different moments of inertia, 2 different cross sections, so it's not prismatic. For 15 feet, it is an I value of 6,000 inches to the 4th. Okay. And for our, I've got a focus problem here. Let me see if I can fix that. I'll try it. Okay, so our I is 3,000 inches to the fourth, and an E is 29,000 KSI, and we want to find then the slope and deflection at B and the slope and deflection at C. So A is the wall, B is the change in property, and C is out at the tip. And we do have a 20 kip load acting up. Okay, so all we do is we draw the M over EI diagram, so this should be no major challenge for us at this point. The moment diagram, we know that the shear is constant with this load, which means that the moment is first order, and then because of the 2I on this guy, we basically half the loads on this. So we get this strange kind of triangular shaped loading on this. Okay, and so our values are that it is minus 200 at this point, it's minus 100 here, it's minus 200 here, and it's 0 there. Okay, and that's our M over EI diagram for the beam. Okay, the next step then is we take our beam, which was a fixed and a free support condition. Again, we're not worried about what B is doing. The only one that matters to us on B is if there's an internal roller or an internal hinge, but that's not the case here, so B just stays free. Okay, so we said that on the real beam that a fixed end became a free end, and on a real beam a free end became a fixed end on the conjugate. So that's all we do is we draw the new structure. The new structure looks like this. Okay, so you can see that A is now free, C is now fixed, B is still what B was. Okay, then all we do is we take the load, the M over EI diagram that we had here, okay, and I apply it as a load to this beam. Okay, so it's a negative M over EI diagram, so the load is acting downward on our beam. Okay, and so this is the conjugate there. Okay, and so now all we have to do is now find the values that we're looking for. So we wanted the slope and deflection at B. All right, so what I'll do is I will take my beam and I can cut this guy at B and then basically solve for the shear and the moment values of this conjugate load structure. Okay, and so you can see right off the bat we can start kind of coming up with some convenient ways of calculating values for more complex loadings on this. Okay, so all we're going to do then is do sum of forces in the Y, tells me that minus VB. Okay, and then I'm going to take the area of all of this, so it's 1/2 of 100 plus 200. Okay, is the height. I'm doing kind of a trapezoidal rule on this thing. So it's 100 here, it's 200 here, and the height of this thing is 15 feet. Okay, and so my area of that then we find out is that VB is going to be a negative 2625 over EI. And the units on this, again, just like with moment area, you got to watch the units, that the numbers that come out of this are kip feet squared on this. Okay, so you'll have to, if you want to solve for actual numerical values, you'll have to convert that foot squared to inches squared in order to cancel out with what's going on down below. Okay, so then for the real beam, because the shear on the conjugate was this guy, the real slope then is the same value. That's it. That's all there is to it. We can go in, we can do the rest of them. Do it real quick. Okay, kind of the same basic game. We do the moment at B. And if I write my equation, we're going to do the moment at B is going to be 100 over EI times 15, the width, times its centroid distance, 15 over 2. Okay, plus then this is the triangle portion, so it's 250 minus 100 over EI, 1/2, 15, 2/3 of 15 for the triangular portion, and you solve for the moment at B internally on the conjugate is minus 22,500 over EI, and again, kip feet squared. Okay, so then the real beam, the displacement is minus 22,500. That's it. That's all there is to it. And we can go through and we can do the exact same process for C. Okay, except now the load gets a little bit more complex. Okay, we can solve for the shear at C, okay, by taking all those areas, and we find out that the shear on the conjugate, and again, I'll leave that kind of as an exercise for you at this point. The shear on the conjugate is minus 3625 kip feet squared over EI. For the real beam, corresponds to, or on the conjugate, corresponds then to the same value on the slope of the real. Okay, and then likewise do the moment, and you can see it starts getting a little bit longer, but it's not hard. It's just basic statics at this point, and so our moment at C ends up being minus 55,420 and kip feet squared, and then all of that over EI is the conjugate moment, which corresponds then to the real displacement. That's it. That's all there is to it. Pretty easy, right? Okay, now with this information, we can kind of sketch what the pictures look like just to kind of test our theory, right? In the original structure, we had a fixed condition here, and it was a pretty stiff member here, and then something a little bit less stiff out on the end. So with a load applied out at the end of this thing, clearly this is going to rotate downward. And so this is going to rotate at some amount, or deflect downward at some amount to here. Okay, but over the same length for C to B, it's going to do even more so. So it's kind of this, it's fairly shallow, and then it drops a lot more because of the change in stiffness in the beam. And that's what those numbers were saying, right? Remember, both theta C was a minus 3625, so that's a negative line, and this guy was minus 2000 something. What was the value? 2620 on that one, so it's less slope at this location, and so that's what you would expect on this. And then the deflections also confirm that this deflection is indeed bigger than this guy, right? So the shape holds up to how we would expect it to hold up. Super, super easy on this. All right, let's try one that's a little bit more involved. Okay, but it's still the same idea. Now, we won't work this all the way through. The hardest part is basically getting the conjugate structure in the M over EI diagram. So now we have a multi-span continuous with a hinge. All right, so I've got a beam that is pin supported at A, has a roller at D, a roller at E, and is cantilevered at F with a point load on the end. And then at point C, we have an internal hinge. And all the distances between these are all 10 foot, 10 foot, 10 foot. Okay, now, to make things super interesting, you can see that this guy has an I of 5,000, and the I of the other member is half that. So this is 2I, and this is I. So if I look at my M over EI diagram, if you draw the moment diagram for this, do your statics and solve for what the moment diagram looks like, you get something that looks kind of like the following. Okay. And so if we look at what we have happening here, then because of our I's and our two I's, we have a triangle load that is 100 over EI at B. Oh, I forgot there's a point load of 40 kips in here. That's why it's triangular. Threw me for a second. Okay. Moment on the real diagram, because it's a hinge, should be 0, and it is. Okay. And then we go and we look at these other two supports, and you get a minus 200 over EI here and a minus 150 over EI here. So again, all these lines line up with, if I bring this down, with all of the major points A, B, C, D, E, and F. Okay. All right. So that's our loading. That's going to be the loading that goes on our conjugate. And then all we do is we come up with our conjugate structure. Okay, and so we play the same game. So remember we said external pin supports don't change. Okay, internal hinges become internal continuous supports. Okay, internal continuous supports on the real system become internal hinges on the conjugate. So that's a hinge now, and that's a hinge. And then a free end becomes a fixed on the conjugate. And so your new structure looks something kind of like this. Okay, and so it's pinned here. It's a roller here because that was a hinge. This is now a hinge because it was a roller on the reel. This is a hinge because it was a roller on the reel, and then that is now fixed. And so that's your beam. And so all I'm going to do is I'm going to take this M over EI and load it onto that beam. Okay, super, super easy. Okay, so now if we're looking, say we're looking to find what I believe it's the deflection at C that we're after. Okay, so we're looking to find the deflection at C. Well, in order to find the deflection at C on the real structure, I'm looking for the moment at C on the conjugate. So our loading then, if you look at our diagram, that we have a positive area here, so that load is going to be acting upward, and we have a negative area here, so that load is going to be acting downward. Okay, and that's what we've drawn here. So this load is up and that load is down. And like I say, on the conjugate beam, sometimes you get loadings that just don't seem real logical. I can't say as on a real structure I've ever had a loading that looked like this. I guess you could with some uplift or something, but don't be surprised to find some kind of strange looking load diagrams. Okay, but the method holds. So now if I want to find the deflection at C on the real system, then all I have to do is know that, well, what was the mapping? Deflections on the real are moments on the conjugate. I need to find the moment at that support. So I'm going to cut it just over the support at C, and that's what I've done here. And so you've got your reaction AY, which in this case we think is acting, what would be, I think I drew it downward. I guess it doesn't really matter, but our real structure. Okay, so I assume downward positive. It's a little unusual for me to do that, but it can be whatever it wants to be. Okay, we don't know the value. We still need to find it. So, and then the structure that you're going to solve then is going to have a free body diagram. It looks like this is the moment at C on member AC. Okay, so that's why, so we've cut it here. Okay, and then the loading is this triangular loading of 100 over EI acting up, and our length on this, I believe, is 20 feet. Looks something kind of like that. Okay, and with that, now this is statically determinate. Once you found AY, you'd have to find AY on this system, but you can do frames and blow it apart and find the support reactions, and then once you have that guy, then you know the moment. And that's all there is to it. And that's the basic approach. Nothing to it. Okay, there is a little bit of algebra that's involved, but that's the method. And so with that, I hope this has made some sense to you. You know, it's all about being able to draw these conjugate structures and get things looking the way they need to with the mapping, and then just remembering the mapping from the real onto the conjugate system. So I hope that's made sense to you. It's a pretty short lesson, pretty easy concept, really. The statics gets a little intense with the loading that's on it, but for now, if you've got any questions or comments, toss us in the comments down below. I'll be happy to answer them. And if you found the video helpful, please toss us a like or a subscribe, and we will see you guys next time. Happy engineering.